So now let's take it all, put it together, and solve a differential equation. So we want to solve y prime plus y is equal to f of t. We have an initial condition, and we know f of t is written as a piecewise function. So our first step really is to rewrite this in terms of the unit step function. So it's going to be 0 in the beginning, and then we're going to jump to 3 cosine of t once we hit pi. So we could rewrite that as 3 cosine of t, unit step, t minus pi. So here's what we have. I'm just going to rewrite that differential equation. So to solve, we have to take the Laplace. So we're going to take the Laplace of each piece. So the Laplace of y prime is sy of s minus y of 0. The Laplace of y is y of s. And then this guy is going to be 3 e to the negative pi s, since that's our a, times the Laplace of the cosine of t plus pi. So this guy is our alternative form for the Laplace. And that's going back to our cheat sheet. We derived that one. It was number 53. Making our substitution in there for a, and then replacing that t with t plus a. Now we really need to simplify this guy. So cosine of t plus a, our a is pi. That's going to be cosine of t, cosine of pi, minus sine of t, sine of pi. We know sine of pi is 0. Cosine of pi is negative 1, so this is just negative cosine of t. And we could pull that negative out. So I'm just working with our right-hand side right now. This was just some scratch work to simplify. So I'm going to box it off. The Laplace of cosine of t is s over s squared plus 1. Now let's go back over to the other side. So we have s y of s minus y of 0, and our y of 0 is 5 plus y of s. And that's the initial condition they gave us here. So that left-hand side is really not changing any in those first few steps. But what we can go ahead and do is factor a y of s out of the first and last terms. So now to get this by itself, we can move the 5. And then divide everything by s plus 1. So then y of s is equal to 5 over s plus 1 minus, and I'm going to reorder this, 3 s over s squared plus 1 times 1 over s plus 1 e to the negative pi s. And we can actually think about this guy more like, and I'm going to rewrite that, 3s over s squared plus 1, s plus 1. So let's do some partial fraction decomposition. Who doesn't like doing that? We need to break this guy down. So we have 3s over s squared plus 1 times s plus 1. So we have, I'm going to do the linear term first, and then the irreducible quadratic. So 3s is going to be equal to a times s squared plus 1 plus bs plus c times s plus 1. So we have as squared plus a plus bs squared plus bs plus cs plus c. So let's create that system. We're looking at s squareds, s's, and constants. We do not have an s squared on the left. That has to be equal to a plus b. We have an s on the left. That has to be equal to b plus c. We do not have a constant on the left. That has to be equal to a plus c. So if we type this in, do RREF, I got negative 3 halves, 3 halves, and 3 halves. So then this guy can be rewritten. So y of s equals 5 over s plus 1 minus, and let's do that rewrite. We have negative 3 halves over s plus 1 plus 3 halves s plus 3 halves over s squared plus 1. And all of that's multiplied by e to the negative pi s. What that means is this guy's going to have a unit step piece. So I'm going to do some distributing here just to make this easier for us to see. I'm going to distribute that negative n and that exponential n. So we're going to have 3 halves over s plus 1 e to the negative pi s. And then we're going to have a minus 3 halves s over s squared plus 1 e to the negative pi s. I am splitting the numerator for this. So notice that too. So several steps happening in that one step there. Now, let's take the inverse Laplace. So inverse Laplace of y of s is just y of t. That's the easy one. This guy, that's your exponential. That's just your standard exponential. Our a is a negative 1, so this is going to be e to the negative 1t. That next piece, remember what everything's telling you. This tells us it's unit step. let's focus on that first. So if we were to find the inverse Laplace of that, it's e to the negative t times the unit step of t minus a. And our a ends up being pi here, because remember it's based off that exponent. So it's going to be a t minus pi. Whatever we put here, we have to replace that t with here. They have to be the same. Let's go to the next one. This guy is cosine. A is pi. So we can rewrite that. We have that negative 3/2. This is cosine of t. Unit step, t minus pi. We have to put a t minus pi here. They have to be the same. And then that last piece, we have a minus 3/2. This guy is your sine. So sine of something. A is pi again in this case. So it's unit step of t minus pi. So t minus pi has to go here. Remember, these guys have to be the same. Now, let's do some simplifying. So, we want to simplify cosine of t minus pi, and we want to simplify sine of t minus pi. So, we're using our sum and difference formulas here. This is going to be cosine of t, cosine of pi, plus sine of t, sine of pi. Sine of pi is 0, cosine of pi is negative 1, so that's negative cosine of t. Sine of t minus pi is sine of t cosine of pi minus cosine of t sine of pi. Sine of pi is 0. Cosine of pi is negative 1. This is negative sine of t. So we're going to make that substitution, and for this guy and for that guy. So side work, I'm going to box it. Y of t is equal to 5e to the negative t plus 3/2 e to the negative t minus pi. If you wanted to distribute the negative in, you could. Unit step, t minus pi. Minus 3/2 times the negative cosine, which would make that a positive. Times unit step, t minus pi. Minus 3/2 times negative sine of t, which would make that a positive. Times that unit step, t minus pi. So, there's our answer. Now, notice those last three pieces all have that unit step in it. It also all has a 3/2 in it. So, let's just simplify that a little bit more. Factor that 3/2 out. And then factor that unit step out. So there's our final answer. Now, we could actually write this as a piecewise function. So I want to do that because I think that's kind of cool that we can do that. And I'm going to do that in a different color. And I'm going to box it in up here. So if we want to write that as a piecewise, y of t. So we're starting with that 5e to the negative t. That works as long as t is between 0 and pi. And then once we hit pi, we are adding this piece to it. So we're starting here, and then we're shifting up 3/2 e to the negative t minus pi plus cosine of t plus sine of t. So we're turning that piece on. And that works when t is greater than or equal to pi. Remember, this guy's going to take on a value of 0 in the beginning, so that's why this zeroes out for that first piece. And then as soon as we hit pi, this takes on a value of 1. So then we would have this guy plus this times 1, which would just be those two pieces added together. So there's that piecewise function. So I want to walk through one more example of solving a differential equation with these. So let's say we have this setup. We have y prime plus y is equal to f of t. We know initial condition y of 0 is equal to 0. And our f of t is this piecewise function. Your first step is to rewrite f of t in terms of the unit step. So in this case, it would start at 0. And then we're shifting up 5 units once we hit 1. So then that can just simplify to 5 unit step of t minus 1. So then now we have our differential equation as y prime plus y equals 5 unit step t minus 1. So let's take the Laplace. So if we take the Laplace of y prime, it's going to be sy of s minus y of 0. The Laplace of y is just y of s. And then the Laplace of this guy is 5 times the Laplace of the unit step, t minus 1. And just going back to our formula sheet, that's going to be e to the negative 1s over s. Now, y of 0 is 0, so that's just going to go away. Let's factor a y of s out. That's going to leave us with s plus 1. So we have 5 e to the negative s over s on the right. Isolate y of s. That's your next step. So y of s is equal to 5 over s times s plus 1 times e to the negative s. So I see partial fraction decomposition again. So let's do it off to the side. So 5 is equal to a times s plus 1 plus b times s. So our system. 0 equals a plus b. 5 is equal to a. If 5 is a, that means b is going to be a negative 5. Box that guy out. So make that substitution. So we are going to have, plugging it in for that a and that b, we have 5 over s minus 5 over s plus 1 times e to the negative s. And we are going to have to distribute that. So next step, now that we've isolated y of s, now that we've split that apart, we need to do inverse Laplace. Now I am going to write this step out. I'm going to pull the 5 out of that first one and write it as 1 over s times e to the negative s. And I'm going to pull a negative 5 out of the second one. Write it as a 1 over s plus 1 e to the negative s. This guy is just y of t. So we really need to focus on this. This just tells us we're going to have a unit step attached to it. So 1 over s, if we take the inverse Laplace, it's 1. And then we're going to have the unit step of t minus 1. Notice our a here is 1. That's coming from that exponent. Now, there's not a place to plug in for t over here since the inverse Laplace of 1 over s is just a number. So we don't have to worry about that for that piece. Here, focus on this. That's e to the negative t. A is 1 again, coming from this exponent. This tells us there's a unit step attached. It's going to be t minus a. Our a is 1. Whatever goes in here for t has to go in here for t. So we could rewrite this as 5 minus 5 e to the negative t minus 1. And think about just kind of factoring that unit step out. So if we wanted to write the piecewise function that this would correspond to, we could think about it starting at 0, as long as 0 is between t and 1. And then as soon as we hit 1, this guy takes on the value of 1. So we're going to have that 5 minus 5 e to the negative t minus 1 there. So it could be really confusing between that S translation and then that T translation, which is also called that unit step function. So I just kind of want to recap that in about 5 seconds. So let's say we want to take the Laplace of a function times e to the at. That's always going to be an S translation. And remember, that comes from applying that definition of a Laplace. Now, if we're taking the inverse Laplace of something, that's a function times something we recognize as a Laplace transform, then that's just a key to let us know that we're going to use a unit step function there. So we saw that unit step in the last few examples. We saw the S translations at the beginning of this section. So just keep in mind which one you're using when. Taking the Laplace of an exponential times something is always going to be an S translation. Taking the inverse Laplace of an exponential times something is always going to be a unit step. So be careful to keep in mind which one you're doing when.